Hello, I'm Dan Alford with ARC Specialties. I'm a roboticist. That means I got the coolest job in the world. I get to travel all over the world, work in 33 different countries, most of the industries. And I've done this for the last 43 years. And in the process, I get to create jobs, which is one of my great joys. But the other thing I get to do is I get to see how other people build things. I get to see how people build things in all sorts of different industries and different geographies. And what I do is we take these clever ideas that we learn, bring them back and reapply them. It's called analogous thinking. Makes us look smart, but it's really just the reapplication of a good idea to a seemingly different but actually similar problem. And that's what I'm going to try to do today with my talk. We're talking about thermal cutting. I'm going to try to give you some actionable ideas for you to be able to take and apply them to your world. These come from all over the place: hydro turbines, shipbuilding, pipe making, all sorts of things, but they could apply to your world, and that's what I challenge you with today, to take some of these ideas and apply them. So, get a history class. Plasma, the first patent that I could find, 1957. This was at Linde. Linde is now called ESAB, but way back then, Dr. Gage patents this plasma technology. This is actually welding, but then it progressed into cutting later. But in the 60s, NASA actually used plasma to test the ablative coatings on reentry vehicles, because plasma is the fourth state of matter. It's ionized gas. So they used it in NASA in the 60s, and that actually caused people to stay involved with the process. And then in 1970, Hypertherm came out with the PAC 400. I actually had a PAC 400 in my shop way back in around 1990. I don't know where it is now, but great power supply, worked great, and it's been going on with Hypertherm, ESAB, Thermodynamics, and a bunch of other companies ever since. This is my personal history with plasma. Way back in 1983, they wanted to do a hot tap up in a smokestack at the chemical processing plant. The problem was it's 100 feet in the air, radioactive, and below freezing. What could go wrong? But this piece right here, that little square, simulates the smokestack. It's 300 series stainless. 300 series stainless can't be cut with oxyacetylene without powder. So the easiest way to do it is with a plasma torch, and that's what you see here. We're cutting through the wall. So we're having to reach 6 foot into a 10-inch diameter tube. We had to weld that tube to the wall from the inside, and then we had to cut the wall out. We weren't allowed to drop that slug because the machine was down at the bottom, and they said don't drop the slugs. You can't hold stainless with a magnet. So what you can't really see here is a suction cup. So this was back in 1983. Worked so well we were called back to do it again in the 90s, but that's how long I've been working with plasma. Over here you can see the actual welding operation. So this is the first operation. We TIG weld. That's me, that's Jeff, way back in the day. Reasons to automate cutting. The three most important things to consider when welding are fit up, and fit up. I see a lot of parts that look just like this. It is a hole, it is a cut, but it's atrocious, and it will require 10 times as much work to fill this up as if you'd made a decent cut. And that's the point of today. The first thing you have to do is start with a good part. This allows us, A, to make an easier weld, and B, potentially to automate it. I'll give you an example. Here at ARC Specialties, we have something we call MAP, Manufacturing Automation Audit Program. What that means is I walk all the way from your receiving dock through your entire manufacturing process to your shipping dock. I get a call from some guys down south of Houston at a place called Easy Line. They said, hey, we want to automate all of our welding on these pipe stands. So they wanted to automate all of this. I said, hey, I'm here. Let's go ahead and do a map. Let's audit your whole process. We started at the receiving dock. We barely got 100 feet in, and I realized they were actually cutting these parts with a magnetic template tracer. There's not many people left that even know what that is. You'd make a part that's exactly the same size as the part you want to cut, and you follow it with a rolling magnetic wheel, which moves a cutting torch beneath it. And I saw this machine, I said, Smithsonian wants this. And so that was our first project. We developed this plasma cutting robot with a feeding table, and we'd feed the I-beam in, automatically cut all the shapes, part it off, full auto, worked great. Installed it a few months later. They called us up, they said, we need another robot. I said, great, we're ready to do the welding robot. They said, no, we fixed the welding problems. All their welding problems went away when we started cutting. So the second robot that I've sold them is another cutting robot. This just reinforces the idea that with good cutting, you can achieve better parts and allow automation if you'd like to. This is actually in our shop. I want to talk about why plasma. On our burning table, we're actually running plasma and Oxy-Fuel. People tell you Oxy-Fuel is an ancient process, it's out of date, but let's compare them. Starting. It's very easy to start a plasma. You don't have to let the metal preheat. You simply turn the plasma on and you've got a cut going. With Oxy-Fuel, you have to wait until you've actually got that base metal up to what we call kindling temperature, because they used to call this burning, because you're actually burning the iron. Iron oxidizes. Iron has an exothermic reaction. So you have to wait until we hit that temperature before we can start. That's one negative part on Oxy-Fuel. Materials, with plasma we can cut almost anything. With Oxy-Fuel, you only cut titanium and steel. Accuracy, this is where plasma wins. We're holding plus or minus 3. We're going to give you an example of that. Oxy, I'm saying about 60 thousandths, about a 1/16 of an inch. Cut thickness, this is where Oxy-Fuel wins. I put the limit around 2 inches. Of course, you can find examples where we're cutting up to 4 inches with plasma. But in my world, anything over about 2, you probably should go Oxy-Fuel. And I've cut 36 inch. The books say 60. I've seen photos of even thicker than that. And the cost of equipment. Plasma is more expensive, and Oxy-Fuel torch is cheap. And so we are going to show you a couple of examples where we're using Oxy-Fuel, and it's either because it's very thick or the customer doesn't want to spend the money on the plasma. So there's still alternatives to plasma, and you need to consider both. So when I talk to people about automation, they always give me these reasons they can't automate cutting. First off, it can't be used in the field. Second, it's hard to program a robot. Third, it's not man-portable. That means you're committed to bringing the part to the robot. Cuts are not accurate enough. Back-gouging with carbon arc is simply better, people will tell me. Plasma works best on steel. Parts must be accurate. Garbage in, garbage out. Carbides and hard materials are hard to cut with plasma. And tapering of plates, that's a machining operation. And it can never replace machining. All of these are wrong, and I'm going to give you examples that prove my point. First, I want to talk about the elephant in the room, the other problem that wasn't on my list, but now you get another history class. Way back in the late 1800s, we started having boiler explosions. This is the old riveted boilers. On a steam engine, you have a high-pressure boiler, and high pressure means they could explode, and they did explode. You can imagine in the early days, material properties were bad, joining techniques were bad. We had a lot of explosions. What's my point? Something had to be done. We had all these widows and orphans running around. It was real sad. So we could either get the government involved, that's never good, or we could create a system of voluntary codes and specs. That is how everything is built to today. ASME, American Society of Mechanical Engineers, created the first voluntary code. It was for these pressure vessels. Guess what? It worked. It worked so well that that is how all codes work. They're all voluntary. You can build a building that doesn't comply with American Welding Society D11 structural welding code, but you'll have trouble insuring it and you'll have trouble selling it. And so this system of voluntary codes and specs has worked really well. Let's talk about the elephant in the room. One of the biggest use of robots in industry is dust collection. People buy them, they don't work, they put them in the back, and they collect dust. And the reason I gave you that history class on the preceding slide is we have a solution to this. It's another voluntary system. The A3, Association for Advancement of Automation, actually has a program to certify robot integrators to prevent robotic failures. Anybody that is a certified integrator, all their programmers have been tested. They have to follow all the codes and specs. And they have to do a safety audit on every system, and they have to maintain records, and they're tested periodically. I'm a big advocate for this, but as with all voluntary codes and specs, until the end users demand it, it's just a voluntary system. But I sincerely believe that A3 is doing great things with their Certified Robot Integrator program, and it will help us to minimize the number of robots that have problems. Okay, let's go back to my list. Reasons to automate cutting. Can't be used in the field. Well, back in 1983, that was the first time I used plasma in the field, so that kind of negates that argument right there. We were plasma cutting up in Idaho, and that first example I showed you. And then let's go to today. This is not a plasma operations, but it's a demonstration that you can take robots out of a factory. There's no reason that robots can't be moved. So these robots are actually operating on a drill ship in the Gulf of Mexico as we speak. These robots are picking up these 50-pound bolts using laser vision systems to find the holes, to find the parts, find the bolts, torquing them to 18,000 foot-pounds. We're taking humans out of the red zone. This is a perfect example. Robots can be taken into the field. Robots are hard to program. Well, here's a really good example we did a while back. I think this is one of Nick's jobs. You know, we're taking a CAD program. Anybody would walk up at the trade show and we'd ask them what their name was, said, my name's Joe. We'd put that on the CAD model and we'd go straight from CAD to cut. There's no intermediate steps. So the robot would then etch in all these letters and then cut. Of course, we had to do it on a pipe just to show off, but we can do this on spheres, plates, any shape you'd like. And then here's the actual cut that we're going to make. So this isn't a universal thing, but frequently, if you have good CAD models or you have the ability for us to do parametric programming, which means you have a family of parts that are all very similar, then we can drastically reduce the programming load. In many cases, we can eliminate it entirely. And this is a good example of using CAD. So here's one. Robots are not man-portable. Here's an example where it actually is. This robot is cutting holes in ships. So you have to cut holes in order to do some work on the hulls. And this thing is entirely man-portable. We have a magnetic base where the human sticks the base onto the steel hull. Then you stick the robot onto that. And then we're plasma cutting the hole. This is an interesting thing, brings up another point. If the robot cuts the part, then the part is accurate. And if the part is accurate, you can automate. And so what you see here is we're actually making two cuts. We cut the inside cut, if that's one bevel angle, and that bevel the part that we're going to use to re-weld it, and we're making the outside cut. And when you do that, you throw away that small ring, and then you have the perfect bevel, the perfect part, and it facilitates the welding of this same part without the need for any adaptive control, like a vision system, laser stripe tracking, through the arc tracking. And that's precisely what we've done now. So after we finish cutting all these pieces with this robot, we simply change it over to a gas metal arc welding torch. We're running a dual shield flux cord wire, and we're allowing the robot to then weld that back up at the end of the operation. So this proves 2 points. Yes, they are man-portable. And second, if you have an accurate cut made by an accurate robot, you drastically reduce the difficulty of welding. As you can see here, we're now able to weld without any adaptive control systems. Another reason to automate, parts are not accurate. This was an interesting job. They wanted to replace laser. The problem with laser is a watt of photons is much more expensive than a watt of electrons, plus it's relatively dangerous from a distance. You know, plasma has its own inherent risk factors, but lasers can hurt you from a longer distance. So what they wanted to know was exactly how accurate can we go. And if you can see right here, we're holding 0.0027. That's less than 0.003 of an inch on circularity. So the robot with plasma can cut nearly as accurately as laser with less equipment costs and less energy costs. And you can hit some extremely good tolerances. This is down near machining quality. Another reason to automate, back gouging must be done with carbon arc. So this is tradition. You use a carbon arc electrode, a gouging torch, and what you see here is we have an arc and we're blowing the metal away with air underneath there. This is the way to remove the back of a weld before making the backside weld. The machining was showing that you could do it with machining, but that's usually a problem, particularly in the field. So here's the alternative. We're using a plasma gouger. Now gouging is a little different than cutting. We're only making a partial depth cut. And so this is the backside of a weld. We've already made the weld on the other side. But before we can weld the back side, they want to gouge down to sound metal. You could grind it, you could machine it, you could carbon arc gouge it. But in my opinion, one of the best techniques is plasma gouging. Because with plasma gouging, you get a nice groove, very repeatable, minimal grinding. It can be done with a robot, and the whole thing can be made portable. This is a great application for plasma. I encourage everybody to look at back gouging with plasma. Wonderful process. Reasons to automate. Plasma works only on steel. Well, here's a great example. These are aluminum castings. There's a lot of interesting things going on here. I'll try to describe them. If you look at that one, we are now cutting all the parts off, and this is all aluminum. This is after casting. You have to trim the casting. You can either do that with a trimming die, or you can do it with plasma. Certainly this wouldn't work with oxyacetylene because it's aluminum. Problem is these castings are not accurate. And the casting, in order for us to hold the tolerances on the cut, we need to know where the part is. So what you'll see here is we're actually using a laser limit switch to find the part. So we're doing laser touch work to find the part, and then after we know where the part is, we can cut pretty fast. And this was a great application. All those pieces you see falling off are going to be remelted and used in the next casting. Great way to trim castings is with plasma. You can see it's all 3D cuts, pretty complex programming, and this was all programmed offline. We had good CAD models, so we knew what the cut path should be, but we really didn't know where that cut path should be located, because depending on the temperature of the part, that could expand or various other problems. So we programmed it all offline. We used the laser limit switch for touch work to register the part, and then we're able to cut quite quickly and effectively. Parts must be accurate. That's true, garbage in, garbage out. If you look here, you notice the customer refused to put any stiffeners inside this vessel. And there's something called gravity. Crushes the vessel. This is no longer round. It's now something of an ellipse. So if I were to cut a round hole in an ellipse, and then when you round up that part, because ultimately they're going to return this to full round configuration, then the hole wouldn't be accurate. So what Kevin's done, and I think this is clever, he's using touch work. If we did it again, we'd probably use a laser, but we're actually using a continuity tester here to determine the diameter of this part. It's still a curve. It's just not the diameter that you would expect for this cylinder. And then Kevin takes all this data that he's collected by touching the part, and he no longer cuts a round hole, he cuts something of an ellipse. But when you round this part back up, all of a sudden that elliptical hole becomes a round hole on the actual part. So parts don't have to be accurate, but you do have to have some way to accommodate this inaccuracy. I thought Kevin's system was remarkable. So here he's doing a dry cut, and we'll let him run an actual cut through this thing. You notice how we're going to pierce straight in? That's a big advantage with robotics. You're able to cut straight in so we can pierce more easily, and then we can switch over to the angle where we have an apparent thickness much higher. Another reason to automate cutting, carbides and hard metals actually cut with plasma just as easy as soft metals do, which is remarkable. This is a piece of drill pipe. This is a tool joint. They call this a box. There would be 30 feet of pipe welded onto this end, and there'd be another tool joint below it. These are simply threaded connections we use in the oil field to couple that drill rig to the rock bit that's drilling several miles below the earth. Problem is this drill pipe is rubbing against the rock, so this tends to wear out. So this is a coating which is made out of steel matrix and tungsten carbide particles, extremely wear resistant. Because it's so wear resistant, it's also very hard to remove. So if you want to re-weld this, you need to remove all of this carbide. You can't weld over it. And so to do that, we're doing it with plasma. But this isn't plasma cutting, this is plasma gouging again. And you can see we end up with a beautiful surface that's ready to weld. There's some surface hardening on this. This is 4137H, very hardenable material. But in spite of that, we have good results because the next operation is to re-weld this to look like that Any surface hardness that was created by the plasma gouging goes away. This has been running in the jungles of Bolivia and South America since the early 90s. Again, proof that plasma technology is applicable on all levels of industry. Another reason to automate cutting, tapering plates. So we're trying to taper this plate. Let's say you have a 3-inch plate and you want to taper it down to 2 inches. How are you going to do that? You have to pick that angle that you want to cut that. There's a lot of material that has to be removed though. And this is a plasma gouging operation. We have a robot up here. We've got a plasma gouger. We're cutting the plate back and forth. Great application. The cool thing about plasma gouging is we can remove over 100 pounds of metal per hour. So do the math. That's faster than anything but the largest machine tools. And it can be done in the field, and it's a very simple operation. Excellent tapering. Another reason to automate, you can't replace machining. This is an interesting one. So these are the Wicket gates on a hydroturbine. On a hydroturbine, you have to control the flow that goes into the runner. And the runner, if you want to reduce the power, you close these Wicket gates. So they close up, and you see the tail of this Wicket will touch the front of that when it's fully closed. When you have two pieces of metal touching each other, they tend to corrode. And so these are all steel Wickets, and if you had steel touching steel, they would corrode. We get sticky Wickets. That's not good. So what we do is we need to machine a groove all the way down the head of this one, kind of like this. So we machine the groove, and then you have to weld the groove up with a material that's corrosion resistant. In this case, it's just a 3/16 stainless weld. You could do this with a machine tool, and you can make the cut, but it requires two operations. You have to put this Wicket on a machine tool, mill the groove, take it off, move over to a welding cell, weld it back up. What we propose is instead, why don't you have the robot do both? We have two tools. We can cut the groove very quickly, very efficiently, and better yet, the robot now knows where that groove is, so then we can efficiently make the inlay weld. Great application, allows one cell to do multiple operations. Plasma can replace machining. This is an interesting one. Now we're going to talk about a lot of different plasma gouging techniques. We refer to it as zero force machining. And there's a real advantage to that. When you're machining heavy materials with heavy cuts, you really have to fixture the part. Here we just lay them on the ground and on the work table, and then we're cutting them. So you can see this is a full 6-axis robot. We're not cutting through the part. This is plasma gouging. We're cutting a groove in here. And so we can remove a great deal of metal quickly. Here we're doing just a single pass, but it's possible to do multi-pass stuff. We can actually start carving parts, and you'll see that here. So plasma gouging, this one I think is a 400 amp system. And look, carving grooves very quickly with a robot with zero tool force. This is the same thing, the tapered plate. I'm going to go ahead and run through it because we've got a much better picture of the part when we're done. So we're tapering this plate, removing a great deal of metal. This is all high strength steel used for hulls. Great process for removing metal. So we started out, I think, with a 3-inch here. We wanted to taper it down to a 2-inch, and we had to do it at a very specific taper rate. Using a robot and a plasma gouger, that's a relatively simple task. And it can be done in the field. It doesn't have to be done on a machine. So you can see we're starting to remove all this metal here. It's gorgeous. I like this one. All this dross is thrown away. Yeah, 3-inch to start. I think we're down to about 2 inches here. Cylinder turning. For example, if you have worn rolls at a steel mill or a cane mill, sugar mill, they don't wear evenly. They tend to wear with bumps. And this is what plasma gouging can do for you. It'll actually take off the high points, round your part back up, get it to be nice and round before you have to re-weld it. So this is a great alternative to machining because we're moving metal much faster than you could do this with a lathe. Beautiful looking parts. You're having to run extremely high voltages, high speed cuts. Works very well though. Let's see, plunging dies. This is something we would think is a great idea because all the dies that are used for both forging, casting, and injection molding are made out of high-strength materials. And so these high-strength materials are hard to machine. So we think that we could plunge these. We could make most of the cut. We could remove most of the metal with plasma. In this case, we're trying to make a die for a bottle. So this is for the glass industry. These base materials are very hard, but plasma doesn't care. To plasma, doesn't make any difference. So we plunge this bottle shape. The final operation would be to do the machining. Early in my talk, I talked about analogous thinking. That's taking one idea from an area and applying it to another. And just to show you that we're actually believing what we're saying, this is our next generation system. We've got an ABB robot. You notice it's at a 15-degree angle. That allows JT to not only work on this cylinder, but on these flat parts over here and give himself full accuracy. He's got this two-dimensional laser scanner, so he's able to find the part, locate it, compensate for any part variation. So this is the next generation system with the next generation programmer, JT, here at ARC Specialties. One more history class. I'm going to nominate Professor Lichtenberg as the father of welding. Everybody says that Davy made the first weld in the 1800s, but in reality, in the 1700s, Dr. Lichtenberg welded a watch spring to a knife edge. So very first electric welder. And the reason I bring this up is because of this quote that I really like. There's no more important rule of conduct in the world than this. Attach yourself as much as you can to people who are abler than you and yet not so very different that you cannot understand them, which is why it's an honor to present this to you today. Hope this helps you. ARC Specialties thrives on problems. Send us yours.